So Colin Bloomfield will speak about Euler universal algebra for first-order logics.
Thank you so much. So first of all, I want to thank the organizers for all their hard work. So far, it's been a lot of fun. And thank you for the opportunity to speak. So this is joint work with Yoshihiro Maruyama. So if you're unfamiliar, the field of abstract algebraic logic provides a unified algebraic framework to classify, prove metalogical results, and develop semantics for classes of propositional logics. So one of the motivations for this is to provide bridges between propositional logics and deduction and results in universal algebra. So, however, the theory is less well developed for first-order logics. And so the general motivating problem is how to extend this theory to include first-order logics. So two of the main challenges mentioned in the literature are, one, a lack of general algebraic approaches to providing semantics for classes of first-order logics. And two, the lack of a suitable notion of formula substitution which preserves logical consequence. So these are two key issues mentioned, and these are two things that I'd like to address. So some background on our syntax. So for us, a first-order language will consist of some collection of propositional connectives and then some collection of quantifier symbols, because we want to talk about quantifiers perhaps besides for all and exists. We will have a multi-sorted model theory. So a signature consists of a collection of sort symbols, a collection of type function symbols, and a collection of type relation symbols. For categorical semantics, well-formed terms and formulas must be in context. And what I mean is that they must include a list of variable sort pairs that at least include those occurring in the expression. So if we do this, we can give a sort of point-free following Levert. We can give a point-free account of classical satisfaction via context. So let S be a classical first-order structure. Then it interprets each sort symbol as a set, each function symbol as a function, and each relation symbol as a relation. Context allows the structure S to interpret all terms unambiguously as term functions. So for example, the term xi, if it's given the following context, can unambiguously be interpreted as the ith projection map, right? And then recursively, if you have a term fm1 through mn in the following context, it is interpreted as follows. You interpret f, and then you precompose it with the interpretations of each subterm, right? So this is when we have a one-to-one correspondence with terms and context and term functions. Well, then S can then go further and recursively interpret all formulas in context as definable relations. So how do we interpret the equality predicate following Levert? We interpret tau, and we take the diagonal, and then we take the preimage via the interpretation of the two terms. And that should just give us the n tuples whose image under M1 and M2 are equal. Other atomic formulas are similar. You interpret the relation and you take the preimage. Formulas of the form phi or psi, well, you interpret phi as a formula, or as a relation, psi as a relation, and then you take their union. Negation is also similar. And this is, I feel like, the really beautiful part. How do you interpret exist phi? Well, you interpret phi in gamma sigma, this context, and then you project out the last coordinate. And so that should give you the collection. This should be the collection of n tuples, where there exists an additional element in sigma, where the corresponding n+1 tuple satisfies phi. Moreover, then we can define satisfaction of sequence in context by saying the intersection of the antecedents is below the consequent. So this gives an alternative semantics for classical first-order logic than the one via valuation or the one via Robinson and flooding the signature with additional constant symbols. So I find this very elegant, it's compositional. And so following Levert, again, now that we've removed points, we can categorify all of these things. So first, the definition, a prop category is the pairs where the first element is the category with finite products, and the other is a contravariant functor from C to poset, the category of all partially ordered sets and monotone maps between them. The motivating example from which this abstraction arose is the following contravariant prop category, where P is the preimage functor. That is, it sends each set A to its power set and each function to its preimage operator. So if you have an abstract or you have a prop category, a structure in it assigns to each sort symbol in your signature an object in the base category C that was a set, right? Now to each function symbol, you give it a morphism in C, and then to each relation, you give it an element in this now abstract partial order of definable relations. Now, that's good, but we want to interpret all of the language of first order logic, so we need to embellish our prop categories with some additional structure. And so first of all, for each object in the base category, P of C has to be an algebra in your propositional connectives, right? If you're talking about, classical logic, then you have to have interpretation of your usual connectives. For each morphism, P of F has to be an L-algebra homomorphism because we're going to think of the images of F as substitution maps. And so term substitution commutes with the propositional connectives. 3, since we're modeling sequent calculi, each of the algebras has to be a monoid. And we'll have an equality predicate. So instead of the diagonal, we'll have these designated equality elements. And finally, here's where we interpret the quantifiers. And so for each quantifier symbol in each object in the base category, you have a natural transformation here. And if you look at for each pair of objects B and C, the component maps essentially map relations, definable relations over B cross C to definable relations over B. And so that sort of models the sort of variable binding operation. And moreover, naturality is because it needs to respect term substitution in a particular way. So here's how, that's kind of a lot of structure. Here's how I like to abstractly visualize this. So downstairs is the base category where you're going to interpret your universes, your sort symbols, and your definable operations like plus and times. You have projection maps down here. And then the contravariant functor goes upstairs. And so P of 1 is your ordered algebra of truth values. For classical logic, this would be the 2-element Boolean algebra. And then over here, you have ordered algebras of definable sets. These would be Boolean algebras in that case too. And in red, we have the sort of images of these morphisms that go in the other direction because they act by substitution. And then in blue, we have the sort of component maps of the quantifiers, which go from relations, say, in n variables to n-1. And then in random places, we have equality elements.
Can I ask a question?
Yes.
What we call prop categories, isn't that something called doctrines?
Yeah, I think maybe post-set doctrines or is another name. This is following Andrew Pitts's terminology, so yeah. Okay, so so then if we have all these extra bells and whistles, a structure in a prop category interprets, and so I'm going to kind of go a little quicker because it's exactly as before with the classical case, except for instead of preimage operator, we have this contravariant functor. Instead of the diagonal, we have this equality element, and then we have our propositional connectives, and then the component maps of the natural transformations interpreting these quantifiers. Moreover, we can define satisfaction of a sequent by, instead of using intersections, we use the monoid operation that we've specified. And then, given a collection of prop categories, they define a logic via the notion of satisfaction. And the thing that was just suggested is that if you look at the logic defined by this preimage prop category, you get classical first order logic. Okay, so just a skim of the literature. So all other work on prop categorical semantics only considers the universal and existential quantifier and fixes their interpretation via stronger adjoint conditions. Moreover, most other accounts assume that the algebras are hiding algebras to model intuitionistic first-order logic. Two exceptions to this in the literature, Shirasu in the mid-90s provided complete prop categorical semantics for substructural predicate logics and used this to prove their disjunctive and existence properties. So that's, I feel like, a very surprising, interesting application. Moreover, Maruyama more recently used them to provide a unified account of various logical translations. So I better give you at least one example of a non-classical quantifier. So I picked this, hopefully it will be relevant to some in the audience. So note that the preimage functor is isomorphic to the Hom functor. And more generally, you can replace that two-element Boolean algebra with any complete lattice V, and you get a prop category with universal and existential quantifiers. They're essentially interpreted as arbitrary meets and joins. In particular, if you look at the closed unit interval, you get semantics for fuzzy logic. And for any T-norm, which is a binary operation which makes the unit interval partially ordered monoid, we get a quantifier defined as follows. So for each fuzzy relation, that's just a map from A cross B to the closed interval 0 to 1. How does this operate? You take the infimum over all finite subsets of B, and then the product over all little u and u. That's a little hard to unpack, but I'll say that min, max, and multiplication are all T-norms, just these operations on the unit interval. And if you look at this quantifier defined with min, you get the universal quantifier. If you look at it with max, you get the existential quantifier. So multiplication or any of the many other T-norms give you non-classical quantifiers. So let FA be the collection of all prop categories, then this naturally defines a logic. And I just want to flash this and say that it has a sequent calculi, and you also add the rules of equational logic. And I just want to say it has this presentation and it's a very weak logic. So you don't need to investigate too closely the rules. So if you ever have any theory, a theory in this minimal logic, so a collection of sequence and equations that are closed under this, closed under the rules of that logic, then you can build a classifying prop category corresponding to the theory, which has a generic T model in that. So that's a structure which satisfies all and only those sequences. So how do we do this? This is essentially what the construction turns out to essentially be like an indexed Lindenbaum-Tarski algebra. So I'll try to sketch it. So for each object, the objects of this base category are lists of context, which are just lists of variable sort pairs. And then the morphisms are lists of terms between those contexts that are equal up to your theory. Given a context, what's the image under this contravariant functor? It's just the Lindenbaum-Tarski algebra formulas in that particular context. And then the image of the morphisms act on formulas by substituting those terms in for the variables. Given that you have a logic that's stronger than this weak logic, you can look at the collection of all classifying prop categories corresponding to its theories, and you will get a logic that's weaker than the one you started with. And so to give a completeness result with respect to this sort of these syntactic structures, you only need to show soundness. And so usually that's the easy direction for a completeness proof, because you only need to check each structure satisfies, well, if your logic is defined by a sequent calculi, you just need to check that each structure satisfies each of the rules. And so given a particularly well-defined logic, it's not too hard to cook up such a completeness result. I'll skip the one that I have here. it's less important. So now this semantics feels algebraic, I hope, but how algebraic is it? And so one nice thing about algebraic logic is that for propositional logic, structures are homomorphisms from the term algebra into an algebra of the same signature. And so I would like to see that structures here are morphic images are morphisms out of the classifying prop category of a theory. That would be sort of the analog. So to do that, I have to talk about morphisms. And so there is a nice definition of a morphism between two prop categories. Since prop categories are essentially contravariant functors, a morphism should be a natural transformation. The only issue is that the base category might be different. So you need to have a product, also a product preserving functor, FO. And so then the natural transformation then completes that triangle. Moreover, we require that this natural transformation preserves the propositional connectives, commutes with the quantifiers, and equality up to a change in product isomorphism. And I'm just going to flash this slide. The important thing is the big picture is that this is actually a two category, and the two cells essentially, let's just say, so this is a two category where the objects are theories, because we have these classifying prop categories. The morphisms will be structures, and the two cells will be structure preserving maps. This all is going well, except there will be one issue, is that the classifying prop categories turn out to not be generic. So there's an issue that they satisfy extra identities not satisfied by all of the prop categories. And I just want to look at the top one. I didn't tell you how the quantifiers are interpreted in the classifying prop categories, and they have to essentially map a formula in gamma prime to one, say, in gamma, where the issue is gamma prime might have more than one variable in this context. And so you have to quantify over all of them individually. I can't see any other natural definition for that. And so that introduces an additional property that's not satisfied by all of the classifying or prop categories. So one way of fixing this, after working this out, I think there's another better way to fix it, is just to impose sort of analogous conditions on the rest of your prop categories. And they're somewhat geometric, but I don't have time to really argue for them. And I'll just say that the prior examples, class of examples we consider satisfy these conditions. So if you add these assumptions, you get some nice results. One of them is that each model of your theory can be identified with a unique morphism. So we really do have this correspondence between structures and morphisms that we have in propositional logic. Two, I'll define the term prop category to be the classifying prop category determined by the LM theorems. So this is sort of the weakest, coarsest such classifying prop category. And it turns out to be a suitable analog of the term algebra. It doesn't satisfy any sort of non-trivial identities. Really, the category of finite products downstairs is just a list of terms. Lindenbaum-Tarski algebras are just formulas. Moreover, if you look at the endomorphisms on it, it determines the natural action of formula substitution, which preserves consequence for each logic that's defined by a collection of prop categories. So I think that's a surprising result, and that was non-obvious and I think overlooked because I think context really clarified. And actually, this was worked out, I think, by it's in a mathematical logic book by Church in the 50s. And so I feel like it's some kind of thing that was maybe kind of lost in the literature. So how algebraic? I want to do two case studies. First of all, I want to look at the homomorphism theorem and then the Hsp theorem. So if you for each logic, I want to let FA sub L be the full sub 2 category, which provides sound semantics for that logic. And I want to say, let E be the collection of all morphisms, right, they have a product preserving functor and a natural transformation, we'll assume that the product preserving functor is full and surjective on objects, and then each component of the natural transformation is surjective. So these will be like our surjective morphisms, and then here, this will be M will be the collection of all morphisms whose product preserving functor is injective, and the components of the natural transformation are order embeddings. These will be our injectives. And so I have a homomorphism theorem result here that says each morphism can be factored as a surjective followed by an injective. And moreover, whenever you have a diagram of this form, Fk, there's a unique completion that's sort of one of the injectives, if and only if the kernel of K is contained in the kernel of F, where you can give somewhat natural definition of a kernel for a morphism. And note that each of these classes form an orthogonal factorization system for the corresponding one category. So then the last result I want to look at is Hsp theorem. And so recall for classical first order logic, if you have a collection of structures, closing them under their common first order theory is equivalent to closing them under ultra products, isomorphic copies, and ultra roots. Okay? And clearly, closing them under products, substructures, and homomorphic images won't preserve first order theory, because you can say something has two elements, product could then have four, you know. But however, in this semantics, we can give a similar characterization. So to do this, though, we'll have to redefine Hs and P. So I'll have to argue that it's reasonable. So let Y be a collection of structures. And recall, we now can identify those with morphisms. So we'll define a homomorphic image is to be post-composing it with some other morphism. And on the left, we'll define a substructure of F to be any morphism where this diagram can be completed by an injective morphism. And then finally, defining products, I don't have to say much, because the product of a collection of structures is the product morphism in the corresponding category. So how algebraic, you have a first order Hsp theorem that says that closure of a class of structures in this semantics, closing them under their common first order theory, is equivalent to closing them under Hs and P in this order for those definitions of an Hs and P. And to finally try to further argue this is that you can use the internal logic of prop categories along with the hybrid homomorphism theorems. One can give a proof that closely mirrors Birkhoff's proof of the classical result. So that's all. I want to thank my advisor, Konstantin Snakis and Adam Prenozel, for their mentorship and many insightful remarks. The preprint is here, and thank you so much for your attention.
I have a question. It's a long time ago, but I seem to remember that if you do the Hsp theorem for many sorted universal algebra, you need to add another closure operator for filtered colimits.
Yes.
So wouldn't that show up in your Hsp theorem as well?
Yeah, I forget the operation you need. I think I think the strange thing that happens is there's a really radically different perspective, because I know in the categorical version of Hsp theorem, the morphisms are two cells essentially. And so here, I think the difference is we're evaluating, say you're evaluating always in the set. Here we have this collection of prop categories. So we're evaluating in different structures. And so we actually interpret it as sort of one morphisms instead of two cells. So like it's kind of quite a different perspective. So
Maybe you can show me later, because this sounds interesting.
Oh, thank you. Yeah. Sorry, I can't I can't fully map out a why, but yeah, I think there's many doubts that I feel like working on this stuff. There was something that is counterintuitive, but I think the way these products and homomorphic images and suboptimals work is very different. So they're somehow encoding like ultra roots and ultra products and isomorphic copies in a different way in this general semantics.
Interesting. Thanks.
Yeah. Yes.
In your notion of prop category, do you assume that the underlying category is plural?
Yes, the base category.
Base category for.
Yeah.
So I'm a bit confused, because at some point you were saying that you can recover things about linear logic, for example. But having products in the underlying category is somehow assuming that the underlying logic is classical, right? So, I mean, it's classical in the sense that I can duplicate variables, I can throw away variables, so. So how does that work?
Oh, sorry, I didn't say, I guess I didn't specifically talk about linear logic, but I
You
think
mentioned at some point that was used for construction.
maybe fuzzy logic or, but
You said you mentioned your.
But I think maybe what happens is, so are you talking about that you get classical interpretations of the quantifiers, or that you get,
No. So you assume structural rules like weakening contraction.
maybe I think there's a different part.
Term, like on the terms, right? Because this is your term language. So essentially, having final products means you can have variable repetition and probably.
I think there's a different perspective in categorical logic where you interpret maybe the proof theory in that category. And so I'm interpreting the logic in the fibers. So I'm modeling the connectives in those partially ordered sets.
Okay.
So
I've got a follow-up question. So again, it's been a while since I've been thinking about this, but I remember like in the classical approach, doing this kind of thing for personal logic, you run up with additional things you have to expect of the quality. I think it's called Frobenius reciprocity, and there's also things like the Chevrolet condition, and I didn't hear that during the talk. So how is that?
And I maybe focused on quantifiers because I think that was the motivating sort of thing to look at. But I really wanted to sort of replicate, see how much results I could replicate and what structure I needed. And so to get these results, I didn't need to impose much on equality. I've looked in a little bit at different kind of notions of equality because I think it'd be interesting. Here you can interpret things like you can interpret it sort of like distance. You know, you use metrics and other things. So yeah, this is the equality you get here could potentially be extremely wild. Yeah. Oh.
So it's part of the philosophy is that instead of trying to get quantifiers as adjuncts substitution, or sort of letting the quantifiers be very flexible.
Yeah. And I want to
nature.
yeah, so this captures some interesting quantifiers, and you can also look at integrals are interesting variable binding operations, and so there are examples where a quantifier can interpret an integral. An integral can interpret a quantifier. But I also want to capture, like, you know, quantifiers in linguistics, and also classic ones about like there exists uncountably many, there exists exactly n. A lot of these things won't be monotone or joint or even monotone. So I want to see, I think a little bit is a philosophical question. What is a quantifier, and what you know, what structures there?
Okay, thank you very much.
Thank you.